Hey, everybody, welcome to Energy Superheroes. I'm excited to have Casey Handmer. He's joining us from Southern California, and he's the founder of Terraform. Terraform's developed a novel way to produce natural gas that's cleaner and better for the planet. Welcome to the podcast, Casey. We're glad to have you.
Thank you. It's great to be here.
So, Casey, tell me about Terraform. I'm really excited to hear this. Most people we talk to are producing hydrogen or some other form of clean fuel. It's exciting for me, having a background in natural gas, to hear that you're producing natural gas. I'd love to hear how you're doing it and why it's different and novel.
Thank you. Terraform Industries is it's a startup, and we're trying to convert captured CO2 from the air into natural gas. And so this has a couple of different advantages, especially when we make money doing it. And the first is that we have a cash flow positive way of rolling out enormous carbon capture capacity all over the world, without having to rely on centralized states handing out vast sums of money to do this, because we've been making money in the process. The second is that the fuel is backwards compatible with existing distribution infrastructure and usage modalities. And of course, we expect to see continuing displacement of some uses of natural gas and fuel with electricity, heat pumps, that kind of stuff. That's all great. Electric cars, that's great. But there's still an enormous kind of existing usage base of all kinds of hydrocarbons that frankly are difficult to displace. And if the key thing is turning down the flow of fossil carbon, that is carbon that came from underground into the atmosphere, into the ocean. We've got to kind of cut that off at the source. And the way we do that is we can build machinery that is cheaper to operate and higher productivity than a natural gas fracked well or a pipeline from some distant country that you may or may not be friends with. And we can do it right in your backyard. And anytime you have enough power, you basically filter the CO2 right out of the air. And at the same time, you're also taking out various pollutants and other nasties you don't want in there, and then just apply copious quantities of electricity to turn that CO2 back into methane.
It sounds really exciting. If you can turn CO2 back into natural gas, definitely an application for that. Could you tell me about your team? Who have you brought on board to help you execute on this?
Yeah, I'm super excited that a lot of the kind of really smart people that I've met over the years when I was at Caltech, or more recently, I was working at a startup called Hyperloop One that was doing magnetic levitation. And I also worked at JPL for a few years. And so I'm just kind of very lucky to have this kind of very rich, collegiate kind of background, I guess, of super smart people. And I think as of now, I think 4 or 5 or 6 people have kind of signed on full time. I guess depends on like when they sign versus when they actually start. But I've got a good friend of mine, Ryan Okerson, is moving down from Seattle next week, where he was working on Starlink, and he's going to be heading up the mechanical engineering part of the company. And then Dr. Stephanie Coronel was a colleague of mine at Caltech who's come on board as a technical co-lead. And then David Smythe, who's probably greatest claim to fame is writing software for the Mars rovers, although he also wrote software for the space shuttle and for the SR-71, is kind of running the business side of the operation right now. So it's a super fun team to work with.
No, that sounds like a really exciting team. In the end, you're trying to solve a big problem, so the execution is really going to be where the rubber meets the road. It sounds like you've got a great team. Let's get into your personal background. You said you were at Caltech. Can you talk your background? What brought you to Caltech? What do you love to do?
Yeah, I'm a physicist by training, and like a lot of my colleagues, basically, found ourselves in high school just being incredibly intellectually curious and just wanting to climb the biggest intellectual mountain available. And at the time, I did a lot of pure math and a lot of applied math, and I did a lot of theoretical physics. I even did some experimental physics, and then over time, basically, I worked a lot in optics. I worked a fair bit in chemistry actually back in the day, and then I came to Caltech and I studied gravitational waves at Caltech, which kind of coincided with the effort to detect gravitational waves there. That was first done in 2015 and subsequently led to a Nobel Prize. Not my Nobel Prize, sadly, but a very worthy team there basically shared credit for that. And then after that, left and went into industry. And Los Angeles is just an incredible city. It's thousands and thousands of companies. It's the world center of 2 enormous industries, both the entertainment industry and also aerospace industry.
No, that's fantastic. Aerospace is big. We've got a lot of aerospace down here in Jupiter as well, with Pratt Whitney being here. And a big focus on natural gas. So it is very exciting that you guys are focused there. What would you say is a word that really describes you well, that describes why you're going to be able to get this done?
Well, our approach with this is to not try and build an incredibly shiny widget that only us and a team of handpicked PhDs know how to build. I mean, there's technical work to be done, right? But we're hoping by the end of this year we'll have a technical prototype that kind of we can show to people, and it exists and it works and it's provable and it uses generic materials. And then really we'll be encouraging our competitors and collaborators the world over to be copying what we're doing as quickly as possible. Because at the end of the day, the overarching goal is to turn off that tap of carbon from the crust into the atmosphere as quickly as possible, and that's going to require tens of thousands of clever people all over the world basically working on it in parallel. And so because the industry is poised to grow by such a huge factor, it doesn't really make any sense for us to worry too much about trying to exclude competitors. That's my belief anyway, especially given that many of those competitors will be overseas and they'll have zero interest in upholding US IP law. So we may as well help them and help us all solve this problem as quickly as possible. And if in 5 or 10 years' time, I've got Chinese and European suppliers who want to sell me subcomponents for my system more cheaply than I can be bothered making them in my own factory, great. The more the merrier. We just need to roll these machines out as quickly as we possibly can all over the world.
That sounds exciting. You're reminding me of Elon a little bit. So you said you worked at the Hyperloop One business?
That's right, yeah. But Elon was not directly involved in that. So
right.
Just to be clear, yeah.
But I believe that he made the Hyperloop IP available to all in a similar fashion. Are you guys going to follow that type of a model for your IP?
I think it'd be more compelling if we actually have like functioning prototype hardware. And also like what we're trying to do is, Hyperloop is almost the polar opposite in that it's a set of like 10 incredibly sophisticated systems that all have to be tightly integrated and work flawlessly. It's a little bit like a supersonic jet or something like that. It's really, there's no room for amateur hour. You can only bake them in one tightly integrated factory with really complex systems. Whereas the systems we're building, we think we'll be able to build most, if not all, of the system in basically any industrial space. And actually, just this week, we finalized the lease on our first facility in Burbank, which is part of Los Angeles, and we have 30,000 square feet there, and that should be big enough to get us through a couple of years of production. We should be able to churn out a couple of hundred units a year there without too much difficulty, and then from there, obviously, grow, because we need to build about 300 million of these over the next 20 years.
That's unbelievable. What was your eureka moment where you were kind of trying to solve this problem, and then all of a sudden you said, "That's what I want to go after"? Was it one moment, or was it a series of discoveries that you made?
It was kind of a series of things. I didn't know very much about gas. I read a couple of books on it probably almost 2 years ago now, and I was like, I guess gas is cheap, but it's not infinitely cheap. It's actually quite labor intensive, and it requires quite a lot of technical know-how in order to get gas out of the ground at all. And in many ways, the United States kind of leads the world in that. And I thought, there's got to be easier things than drilling holes miles deep underground. And so I began to think about this problem. It was quite foreign to me, actually, to think about how do I take a system and optimize it for cost rather than for performance, which is typically what most engineers are trained to do. And typically that means, if you've got two competing systems and you're trying to decide which is best, and one of them is like really simple and basic and just basically badly designed, and the other is like really complicated and fancy and very high performance, high electrical or energy efficiency, you go with the stupid one. You go with the really basic one. And you see this all the time, actually, in just everyday engineering and stuff. Like if you look at how RVs are built, for example, like it's very cost conscious design structure there, and that makes a lot of sense for what they're trying to do. And that's kind of what we're trying to do now, which is take a whole bunch of people who spent their careers optimizing stuff that has to fly to space, and then train them to apply that intelligence and that brain to thinking about this problem more generally. And just to go back to your question about the kind of the aha moment or the eureka moment, it's kind of this problem, which is you want to capture a bunch of CO2, you want to make money while doing it. The CO2 is not worth that much, especially not in the quantities that we're going to need to capture, which is like billions of tons a year. So what do you do with it? Well, what else do you need billions of tons a year of? There's not that many things, and one of them is hydrocarbons. So if you could turn it back into hydrocarbons, then that's great. But how do you do that? Well, there's chemistry involved. It turns out you need a lot of electricity to do it, like way more electricity really than you could get by burning the same quantity of hydrocarbons and turning it into electricity. So we're kind of doing the inverse process. And that's only really possible if you can get really, really cheap electricity. And we're very fortunate, as a species, that solar power has gotten cheap enough in time to make this happen. And that trajectory is kind of continuing in a way that I think over the next 10, 15, 20 years will kind of solve this problem. So you've kind of got these three interacting components, which is like way too much extremely cheap power and nothing to use it on, right? And then a bunch of CO2 in the air that is hard to capture and hard to do things with. And even if you could capture it, what are you going to do with it? Like, it's gas, you can't exactly like pile it up somewhere. But if you could pile it up, that'd be great. Make like a couple of giant mountains every year. And then obviously this enormous unserviced demand for hydrocarbons all over the world. And I should add right now that in the Southwest United States, we don't think we'll be able to break even in terms of cost until probably 2025, in terms of trajectories of solar panel costs and stuff. But today, if there was enough excess solar power available in Europe or in Japan, in East Asia, practically anywhere on Earth that isn't, a couple of states away from Texas, that they could be using a process like ours right now and making natural gas more cheaply than they can otherwise get it. So if you're talking 50 to 100 bucks per 1,000 cubic feet, we can beat that right now. Our process, the process that we intend to share with the whole world, can beat that right now. All that they need is to have tens to hundreds to thousands of gigawatts of spare solar power lying around, which they don't have. And so just over the last couple of months, I've increasingly realized that there's two halves to this problem, and one half of the problem is what we're doing, and the other half of the problem is accelerating the production rate growth of solar photovoltaic all over the world. We can no longer depend on just the rate at which China is able to manufacture these cells. We should be building factories that make them in every country on Earth.
No, that makes a ton of sense. It's really exciting. One thing it makes me think about is, so there's a lot of solar and wind that's going to get built around the idea of creating green hydrogen, right? So I think to the degree that your process can be more cost effective than making green hydrogen, to me, that's more the benchmark that you should look at, because the wind and solar is going to get built out.
We're making green hydrogen. Like, just to be clear, our process will make more hydrogen than everyone else put together. It's just that because hydrogen is hard to transport, what do you do with it? Well, we combine it with carbon, and now it's methane, which is easy to transport, and we have existing infrastructure to do it.
That makes any sense. Okay, that makes total sense.
I love hydrogen, and I have 3D models of Zeppelins hanging in my garage, and I think it's an amazing chemical for all kinds of reasons, but it is hard to transport, it's hard to handle. And so in our system, our electrolyzer is basically piping directly into a reactor. We only have 10 meters of piping to worry about, as opposed to rebuilding our entire continent spanning pipeline systems to deal with hydrogen, which even NASA struggles to deal with. Their giant rocket they were testing last week, they had hydrogen leaks all over the place. So it's a kind of a pernicious molecule to deal with at scale.
That makes total sense. We've had a lot of conversations with folks around the challenges of transporting hydrogen. We've seen lots of different ideas around it, and obviously pulling up the entire pipeline system and rebuilding it is not a good idea. So I think I've seen things that are a pipe within the pipeline. We've seen lots of different ideas, but never one that,
well, I think it should be tried.
Yeah,
I can't say for sure which system will work, but I think what I would really want to see is thousands of companies jumping up all over the world, trying everything anyone can think of. So we'll have companies doing electrification, we'll have companies doing battery manufacture, we'll have companies making photovoltaics, we'll have companies making new wind turbines, better, cheaper, bigger, faster wind turbines. We'll have hydrogen transport. I personally am not going to spend much of my time worrying about ammonia, but other people who like it should, and they should think about how to use it. And actually, I do see a future for hydrogen usage in industrial processes where it is generated on site. So you can have copious green hydrogen generation locally with photovoltaics providing electricity, and then that hydrogen is piped, say, directly into a steel mill. So you don't have to worry about building an enormous 1,000-mile long pipeline across the country. It's just there.
Yep, 100% agree. There's room for everything. We're working on a blue hydrogen project that's extremely exciting, and can deliver it today at a price that's cost competitive. So you see a lot of different opportunities. There's opportunities in biogas, opportunities all over the place to help reduce that 51 billion tons, because as you say, it's a massive problem. And I think you, being an engineer, realize the volume of it. It's easy to say 51 billion tons, but I saw a statistic that said that the entire oil and gas industry today moves about 5 billion tons of matter. So if you think about 10 times of that, trying to move it around and deal with it, as far as CO2, it's an enormous amount.
Yeah. Well, I mean, something like 75% of the weight of the CO2 is the oxygen that comes out of the air when the stuff is burned. I could probably do that calculation more precisely for your viewers, but it's 12 divided by 44, whatever that is. It's just like 73% or something. That's where a lot of the mass comes from. But really, in terms of the energetics, capturing the CO2 is not the hard part. Capturing CO2 is difficult from a kind of materials and construction standpoint. But for what we're trying to do, we're trying to build megawatt scale rigs that we can build $50,000, which is like the cost of a mid quality car. So we can build millions of them really cheaply, and so we can pay them off in a year or two, which means that they'll be their project finance will be comparable to a fracking well or a Bitcoin mining rig or something like that. So we don't have to go out and ask governments to create new loan products for us so that we can pay this off over 30 or 50 years. We have to be able to basically put money in and get money back out, pretty quickly, so that we can support really fast scaling.
That makes tons of sense. What's your, speaking of finance, what's the model to finance the company?
Well, I mean, essentially, like right now we're very early days, kind of just signed our first lease this week, and we've only raised a seed round. So overall, like we kind of have to demonstrate technical, feasibility, and then we have to show that we can manufacture these things cheaply enough and reliably enough, and actually deploy them, and customers will buy our things. So there's a few milestones to hit along the way, and we need to be clear-eyed about these challenges. But long term, I mean, I would imagine that Terraform will be producing natural gas and selling that directly, but we'll also be producing the machinery that produces natural gas and selling those, and we'll also be selling finance products to help people purchase those things, and we'll be selling maintenance services, kind of everything kind of in that general ballpark. So there's kind of a whole set of kind of different levels of this thing, and ultimately we may be selling the factories that produce the machinery that ultimately produces the gas, because at the end of the day, like if you want to grow as quickly as possible, you need to jump up a few levels of abstraction to kind of make that happen as quickly as possible. If I have to sit there personally, like wiring together systems, there's a fundamental limit to how fast we can build this. But if we can cut the ribbon on a new factory every day for the next 5 years or something, then ultimately the production rate of gas will go up as a quadratic of the rate at which we can roll out factories, right? Because each factory produces a set number of machines per day, and then each machine produces a set amount of gas per day. So the net amount of gas produced as a function of factories produced kind of ramps up very quickly. I wouldn't say exponential, but it's certainly
it sounds exciting, and I'm quite certain that you guys can benefit from partners in industry, that are used to doing some of these big size applications.
Yeah, I mean, we have to be set up. We have to be prepared to vertically integrate, right? Just as Tesla had to be when they found out that their suppliers weren't able to basically meet the level of their ambition and their scale and their financing structures. But I'm not wedded to the idea of building Terraform Industries to be a giant vertically integrated company like Tesla. It seems like it's kind of a pain in the ass, and ultimately it will limit scale. I mean, like long term, I want there to be tens of thousands of companies that feed every part in the horizontalization and verticalization of this industry, just as we have with the oil and gas industry right now, where there's thousands and tens of thousands of companies all over the world that all do little pieces of the puzzle, and you can kind of pick and choose which parts you need for a local development. And so there is no one size fits all. It's just kind of a huge industry that's poised to grow. Revenue will be trillions of dollars a year, as it is right now for oil and gas. Ultimately we will probably be producing a little less than we are right now, because electrification will displace some usage, and the unit cost of the gas and the oil that we produce will also be less. Ultimately, we'll be producing oil more cheaply than you can get it out of the ground. But there'll also be substantial costs involved in scaling up, and like a lot of money in basically building machinery and building facilities and building solar farms. So overall, it's $1 trillion industry for sure.
It's a huge vision and very exciting. Can you tell us
and it has to happen? Like even if Terraform completely screws up somehow, we're intending not to, but even if we do, the solar power is already so cheap that it is cheaper in many places on Earth to turn solar electricity into hydrocarbons than to turn hydrocarbons into electricity, if that makes any sense. So
absolutely
so
makes sense.
Physical inevitability that solar power will displace oil and gas drilling. Right, all the downstream stuff like delivery and so on, that will remain more or less unchanged. But it is inevitable that across the entire world, the cheapest way to get carbon, reduced carbon for all kinds of processes, whether that's combustion or chemicals or whatever, will be from the air right around us than from miles underground, especially if you don't happen to live like right on top of the Bakken Formation.
It makes a lot of sense. Absolutely makes sense, especially as we see geopolitical challenges over in Europe and other places. So it's very interesting.
I mean, like people sometimes complain that there isn't enough solar power in Seattle or somewhere, something like that. Well, Seattle's kind of a cloudy place, but it only has like 2 or 3 times less solar than Los Angeles, where I live, and there's plenty of sun here. It's one of the sunniest places on Earth. Now imagine if someone said, "Oh, well, Seattle's no good. It's only got 1/3 as much oil as Saudi Arabia," right? Like 1/3 as much oil as Saudi Arabia would be plenty of oil for anyone. And so we just have to realize that the distribution of solar power of the Earth, especially where people live, is almost uniform by comparison with the distribution of where oil and gas happens to be. And so I think in the future we'll see a lot more local production and consumption of hydrocarbons as well, which is
For
good, I
sure.
think, for global security.
No, it makes a lot of sense. How do you address the energy density challenge of solar? As far as you need a lot of land in order to produce large scale amounts of, let's say, I'm thinking green hydrogen. You need a lot of land to produce a lot of green
Yeah.
hydrogen. Um,
Yeah. I
so
mean, to put it in perspective, right now, I believe these numbers are correct. They may be incorrect, but I think the United States uses about 50 million acres to produce soybeans and corn for biofuel, right? 1 million acres would be enough to displace all current electricity production. So 2% of what we're currently using. And the thing is, the land that we could use for that doesn't have to be arable land. It doesn't have to be, our flawless Midwestern, incredibly deep black soil, which we can grow things on like the envy of the entire world. The United States actually has huge amounts of land, which is not really being used for very much at all. It is not very economically or agriculturally productive. And even though displacing all hydrocarbon production would require quite a lot more solar energy, maybe 10 times more than just displacing all electricity production, the total amount of land is not a constraint. The per capita usage of energy would have to grow by like a factor of 100 before land became a constraint. And maybe that will occur to our grandchildren's grandchildren. That'd be cool because they'll be flying rockets to space every day. But that would be, it's a nice problem to have long time in the future. So I think
yeah,
ultimately, we have to get used to the idea that we have to pave vast tracts of desert with solar panels. And yeah, like there's always an impact, right? But that impact is going to be a lot less than if all our coastal cities drown due to rising sea levels. So that's, you kind of have to pick your poison in that regard. And I think solar panels are way lower impact than alternatives.
for sure. Yeah, it makes a ton of sense. And the key point is that you're making natural gas, which is ultimately transportable. I think the challenge came in with putting solar panels in the desert because you have to have, for when you're using it for electricity, you need transmission towers. And it is very difficult to transmit all that electricity from the desert back into the cities. But when you have natural gas and you can transport it, it makes it a lot easier to put massive world scale solar farms out in the desert because you can move a fuel like natural gas, whereas it's more challenging to build out new transmission capacity to move electricity.
Yeah, I think we'll need a balance of that. I mean, on the electricity front, I've got a blog about this, which people can look up. It's called the Unstoppable Battery Onslaught, but it basically points out that we're production limited as far as battery deployment goes for the foreseeable future, because no matter how many batteries you put on the grid, you can always make money doing it. It's kind of bananas. It's like Superman going to a casino and like using his laser eyes to see through the cards. Like, can cheat completely, and there's nothing anyone can do about it. And so, in terms of like the exact dynamics of demand, but I think long term we'll see much reduced demand for extremely long distance power transmission. So I think like the very large integrated grids and very high capacity transmission lines, both oil, gas, and electricity that kind of span continents will go away because we'll have more robust local storage of power for diurnal or even a couple of days storage. And then on the solar front, solar will be so cheap that we will just overproduce. We'll have enough solar panels out there that we can produce enough power on a cloudy winter day. Then in summer, of course, power will be incredibly cheap. So like even cheaper than it already is, which will come in handy if we have seasonal demand for power for things like aluminium smelting, or in summer we want to desalinate a whole bunch of water and use it to irrigate crops which are no longer being fed by glacially fed rivers because the glaciers have melted. Things like this. But I'm talking kind of 2040s plus at this point. But just kind of long term, I wouldn't be personally betting my own money on long distance power transmission.
Yeah,
or gas or oil transmission for that matter.
yeah. I think your vision is smart. Can you talk at all about your investors, the guys that invested in your seed
Yeah, I'd love
round?
to. Yeah, we're super proud to say that I happen to know Patrick Collison personally, who's one of our investors, Annette Freeman, by my wife originally. And for your listeners who don't know, Patrick Collison's a co-founder of Stripe, which is an internet payments processing company. And their mission is somewhat aligned with ours, which in that it's to increase the GDP of the internet, and basically to realize that as you bring communities of potential entrepreneurs into our modern economy, you can do so via the internet more efficiently than you could in the past. And I think their track record kind of speaks to the success of that vision. And so I made the mistake, as a joke, but I made the mistake of mentioning to Patrick and a few other friends that I was working on this more than a year ago. And Patrick very generously offered to underwrite some of the costs that I was incurring just in my own garage on my own time and money, just buying machinery and running tests and things. And he said, yeah, all I want in return is just keep me up to date. Like every month, send me an update, note of what you've been doing or something. And I think maybe his strategy was to like encourage me to convince myself that it was worthwhile quitting my comfortable job at JPL working on spacecraft, which is kind of a lifelong passion of mine, to actually make this happen in the real world. And then once I said I was going to do that, then he and a couple of his friends got together, including Nat Friedman, who was formerly the CEO of GitHub, and wrote me a $5 million check, which like in the world of VC, $5 million is not a huge amount of money. But if you add up like what my salary would have been for the rest of my career, it's about $5 million. So it's like, it's kind of crazy to have someone be like, here you go. And obviously, like, I'm not, using that to fund, silliness. Like we need to be fiscally efficient. That's the whole point of our business. Like what Terraform is trying to do is actually extremely high productivity, low margin material manufacturing of stuff, which is, really frankly very unsexy. It doesn't really have the ability to get extremely huge and profitable like say Google or Netflix or something like that, because there's no ability to kind of do this, one person writes a piece of code and then 100 million people use it kind of thing. But we can still, I think, exploit a lot of the lessons of Silicon Valley and in terms of how we go about solving this problem. So
it's an exciting time, and you're seeing more and more Silicon Valley entrepreneurs come into the energy industry. I kind of did it backwards.
I think right now we're entrepreneur limited. Like it seems to me that there's more money than founders right now. So if you are a person listening to this, or someone who's interested in this, like I'd be happy to talk to them. Like let's get some ideas going. As I said, I think there are hundreds of business models out there that need to be explored that really aren't being right now. In particularly in solar PV manufacturing, that's what I'm worrying about this week, but also in synthetic fuel manufacturing. And there's a handful of startups which are working on it right now. But as I said, the industry is going to be big enough to support 10,000 companies. So like, let's get to work.
Yeah, I would say we're entrepreneur limited and project execution limited. Because as you mentioned with Google, there's a large there's a challenge in going from a line of with Google you can go from a line of code to a scalable business, but all this stuff is physical. So it takes more time to identify, site, and execute on projects. And so there's that component of the intellectual side and then the project side. And I'm very interested in looking on financing structures that accommodate both sides, because it is different from the pure traditional venture capital model. You have to have this sort of fund the IP approach and then also fund the projects approach.
Yeah, absolutely. Yeah.
So, well, Casey, this has been fantastic. Before you go, are you reading any books? Is there anybody that you look up to that inspires you, or are you just sort of head down in the science at this point?
I mean, I try and read a lot of books. I tend to go in spurts where I'll read like 20 books in a row and then I'll write 20 blogs in a row or something. It seems to use the same part of my brain and I can't do both at once. But just recently I finished reading a book called The Alchemy of Air, which is a very nicely written kind of historical retelling of the history of nitrogen fixation, which was developed primarily in Germany prior to the First World War and then expanded and complexified up into and through the Second World War. And it's like all history, and particularly in this case, it's kind of complex because a lot of the key characters were involved in also developing chemical weapons, and may or may not have been members of the Nazi regime, and there's all kinds of complications there. But on the technical side, they did work out how to go about making chemicals that are essential for fertilizers and also explosives, that Germany and frankly most of the world that did not have like a huge navy was unable to get access to. Because the main source for this was in Chile and islands off the coast of Chile, just where like people used to mine it, right? And prior to that point, prior to this being developed, I think the carrying capacity of the Earth would have been about 3 billion people. So right now, like more than half of the world's population is supported by agriculture, which is supported by artificial nitrogen fixation, which at the time was built in these absolutely colossal plants. That they kind of still exist in Germany, covering like 5 or 10 square miles, like just enormous chemical plants, and they were fed primarily with coal, which is what Germany's default source of cheap energy was at the time. And what we're trying to do is, kind of on a similar scale. Ultimately, we're skipping the chemical weapons and we're skipping the genocides, but ultimately we're trying to find ways of taking chemicals that are in the air, that are freely available anywhere on Earth in abundant concentrations, and turning them into more useful forms of energy to help people avoid scarcity and avoid starvation and discomfort from a lack of available energy, and at the same time also provide a real world mechanism that can stabilize the atmospheric CO2 concentration and the level of greenhouse heating in our atmosphere, which is super important if we don't want to find large swaths of the Earth's surface to be unlivable in our lifetimes. So it's kind of a mixed bag there, but it's been done before, and even today, there's nitrogen plants all over the world that do this, and it's super important for agriculture.
That's super exciting. The Alchemy of Air. You guys should check it out.
Thomas Morris, I think, is the author, but I don't quote me on that.
Hit Amazon, and we're not sponsored by anybody, so that's a free recommendation with no qualifications on it. We're excited to have Casey Handmer here today. He's from Terraform. They have come up with a novel way to produce natural gas that's cleaner and it's better for the planet. It's a revolutionary approach. I think you're going to hear a lot more from Casey in the future. It's been exciting having you on Energy Superheroes, Casey, and look forward to following up and checking how the company's doing down the road.